In this video, we're going to talk about the solubility of a solute. These are your learning targets. In our previous video, we talked about a substance being soluble or insoluble. Remember what those two words mean? Soluble means that a solute can be dissolved in a solvent, whereas insoluble means that a solute cannot be dissolved in a solvent. And in this video, we are going to discuss the solubility of a solute, which is the maximum quantity of solute that can dissolve in a certain quantity of solvent at a specific temperature. So how do we know, first of all, that a solute can dissolve in a solvent, or which solutes can dissolve in a solvent? Well, we talked about the solubility chart and how we can predict certain ionic compounds to be soluble and insoluble. So in addition to that, we are going to learn this general rule, like dissolves like. And again, this is a general solubility rule. It tells us that polar solvents can dissolve polar solutes. Polar solvents can also dissolve ionic compounds. And then nonpolar solvents dissolve nonpolar solutes. So we're going to review how to tell if a substance is polar or nonpolar. But again, just to reiterate, like dissolves like, the solute and solvent both have to be the same polarity. So both of the solute and solvent need to be nonpolar, or both the solute and solvent need to be polar or ionic. This is the reason why oil and water don't mix. Oil is nonpolar, whereas water is polar. This goes against the solubility rule, like dissolves like. So let's review these three words, ionic, polar, and nonpolar. First of all, what's the difference between these words? Well, polar and nonpolar substances are covalent molecules. So ionic compounds are made up of cations and anions, something that's positively charged and something that's negatively charged. For example, magnesium 2 plus and nitrogen 3 minus. From that, we get magnesium nitride. Well, our covalent molecules, we would first draw out the Lewis dot structure, and if we see lone pairs, so remember lone pairs on a central atom, or different outside atoms, we know that we are dealing with a polar molecule, whereas nonpolar molecules have no lone pairs and they have the same outside atoms. Now, I could go into it, and we talked about polarity that has to do with electronegativity, right? But this here is just our simple test of if a molecule is polar or nonpolar. So just to review, when we talk about lone pairs, we're talking about, for example, like oxygen in the middle, and if we had chlorine on the outside, these lone pairs are on our central atom here. Okay. The different outside atoms would be if, for example, chlorine was something else like fluorine. Those are different outside atoms. That would also tell us that it's a polar molecule. Whereas nonpolar, it has no lone pairs and it has the same outside atoms. For example, methane. Okay. Methane has 1 carbon and 4 hydrogens and no lone pairs and same outside atoms. So let's discuss why polar solvents dissolve ionic compounds. Well, ionic compounds, we just talked about, consist of a cation and anion, which is positively charged and negatively charged. So if you take a look at this picture here, here's our positively charged cation and our negatively charged anion. Well, when it gets dissolved in, for example, water, because water is a polar molecule that we've known since biology. Well, polar, we know there's a partially positive side and a partially negative side, right? We didn't talk about this in our previous slide, but we did talk about it when we learned about polarity back in the unit when we talked about Lewis dot structures. So this has to do with electronegativity. And so what's going to happen here? Well, the partially positive side of our polar molecule, our covalent molecule, will be attracted to the negatively charged anion. Okay? Or the negatively charged part of the covalent molecule will be attracted to the positively charged cation. And so if you look at this picture over here, you see that the cation is attracting all the partially negative sides of our solvent, right? And if you look here, there's the anion that's attracting the partially positive side of our solvent. So that's how polar solvents are able to dissolve ionic compounds. So let's take a look at this practice problem. Which of the following compounds will be able to dissolve in water? First, determine which ones are polar, ionic, and nonpolar. Now, the first thing you need to do is really draw Lewis dot structures for those molecules that are covalent, right? Ionic we know is ionic because it has a metal and a nonmetal. Covalent has everything nonmetals. And then once you figure that out, you're able to apply it to the general solubility rule, like dissolves like. So let's take a look at our solvent, water. Now, I know you know what it already looks like, but just for the sake of reviewing, I'm going to go ahead and use this to review. So if you look at water, the first thing we have to do is, once we realize that it's covalent, we need to add up our valence electrons, right? So we have one from hydrogen, and there's 2 hydrogens there, so it's times 2. Oxygen has 6 valence electrons, so 6 plus 2 is a total of 8. So the first thing we want to do is put our single atom into the middle. So we have oxygen in the middle, and then we are going to place the other atoms on the outside. So here we have 2 hydrogens, and we're going to make a bond between the outside atoms and the central atom, right? So each bond we have 2 electrons, so a total of 4 electrons, and I'm going to subtract that here. So we have a total of 4 that we're working with. So remember where these 4 go. Hydrogen doesn't want it because hydrogen wants a maximum of 2. So these 4 electrons are going to go right around the O. And that used up 4 electrons. We have no more to work with. Are they all satisfied? Yes, hydrogen is satisfied with 2. Oxygen here has 8. So there is our Lewis dot structure. So is this polar or nonpolar? Polar because of the lone pairs. So we said water is polar. So now let's take a look at our solutes. First one is sodium chloride. Well, I hope you're not drawing this as a Lewis dot structure because we first recognize that sodium is a metal and chlorine is a nonmetal, so that tells us that this is ionic. What about CCl4, carbon tetrachloride? Well, this is not a metal, so we know that it's covalent. So you would draw out the Lewis dot structure. And assuming that you're drawing it out right now, that you're pausing the video and drawing it out, you would find that carbon tetrachloride is nonpolar. What about ammonia, NH3? Again, another covalent molecule. You're going to go ahead and draw out the Lewis dot structure, and we see that ammonia is polar because the lone pair is on nitrogen. What about magnesium fluoride? Magnesium is a metal. Therefore, this compound here is ionic. What about the last one, carbon dioxide? Carbon dioxide is a nonpolar molecule. Okay, so we figured out that our solvent is polar, and our solutes, we figured out ionic, nonpolar, or polar. So which ones will be soluble in water? So now we want to go back to our general rule, like dissolves like. So remember, if our solvent is polar, what can polar solvents dissolve? Polar solvents can dissolve polar solutes, and it can dissolve ionic compounds. Okay, so if we take a look at the first one, can sodium chloride dissolve in water? Yes, it can. Polar solvents will dissolve anything ionic. Will carbon tetrachloride dissolve in water? No, because one is nonpolar and the other one is polar. Will ammonia dissolve in water? Yes, it will. Will magnesium fluoride dissolve in water? Yes, it will. Will carbon dioxide dissolve in water? No, it will not. Now let's take a look at the 3 factors that will affect solubility. Previously we talked about the solubility chart, and anything that's on this chart is anything that says soluble can be dissolved in water, and anything that is insoluble, remember on the top part, that's the exceptions, or on the bottom part where it says insoluble, it means that it can't dissolve in water. Well, that's just the nature of the solute and the solvent, and that's our first factor that affects solubility. So in addition to the solubility chart, sometimes we can just dissolve more of one compound than another. So in this example, I give you lead 2 chloride. While we can only dissolve 1 gram of lead 2 chloride in 100 milliliters of water, for zinc chloride, we can dissolve 200 grams in 100 milliliters of water. And that's just the nature of the solute and the solvent. The second factor that affects solubility is temperature. Generally, an increase in the temperature of the solution increases the solubility of a solid solute. Think about dissolving salt into water. If we have ice cold water and we try to dissolve 5 grams of salt into it, how much of it do you think will actually dissolve? Not that much. So what can we do in order to dissolve more? Well, if we increase the temperature, couldn't we perhaps dissolve all 5 grams of the salt? Possibly, right? Depending on how much water we're working with. For all gases, solubility decreases as the temperature of the solution increases. So think about a soda can left in your car in the middle of summer. Let's say it's like 100 degrees outside Fahrenheit. And you left a soda can in there, and it was in there for maybe, let's say, 2 days, and then you found it and you popped it open. What do you think is going to happen? No, it's not going to explode if that was your first thought. Actually, nothing will really happen. All the fizz will probably be gone. And the reason for that is because as the temperature goes up, well, the gas that's in the soda will escape from the liquid. And so that's why we like to keep our soda in the fridge. We like it as cold as possible. The third factor that affects solubility is pressure. For solids and liquids, change in pressure doesn't really affect the solubility, right? When did we talk about pressure? We talked about pressure with gas substances. So here we're talking about gas solutes. Well, for gas solutes, an increase in pressure increases solubility, and decrease in pressure decreases solubility. And this is the reason why when soda is made, it has to be done with lots of pressure, right? Well, I mean, and think about it, when you shake up a soda can, what's happening? You're increasing the pressure, right? You are increasing the solubility as you do that. And that's the reason why when you pop it open, that's why you basically have your soda explosion. So, just to bring it all together, for most substances, solubility increases as temperature increases. In solutions involving liquids and solids, typically more solute can be dissolved at higher temperatures. This does not hold true for gases. For most gases, the solubility decreases as temperature increases. And so we're about to look at a solubility curve that shows exactly this. And if you look at the curve on your paper or the curve on the screen, this is a typical solubility curve. It kind of looks like a spider web only because it's showing you many different solutes. So a couple things to note. Here on the Y, we have grams of solute dash 100 grams of water. So this is how much solute can be dissolved in 100 milliliters of water. Okay, so 100 grams is equal to 100 milliliters because the density of water is 1 gram per liter, right? I mean 1 gram per milliliter. So again, this is grams of solute that's being dissolved in 100 milliliters of water, while on the X we have temperature. So you see, for example, if we are looking at potassium nitrate here, okay, and we're looking at 50 degrees. So at 50 degrees, how much of potassium nitrate can be dissolved? Well, that's right around 60 grams. So 60 grams of potassium nitrate can be dissolved at 50 degrees Celsius. What about sodium chloride? Sodium chloride at 50 degrees you can only dissolve, not only, but you can dissolve about 38 grams in 100 milliliters of water. So this tells us a saturated solution. So remember those words: saturated, unsaturated, and supersaturated. Saturated, at this temperature, this tells us the saturated solution, meaning that this is the maximum amount that can be dissolved in a given amount of solvent. Remember, if you go under it, that's unsaturated, meaning you can dissolve more. And if you dissolve way too much, then that's supersaturated. And by then, you would see some crystals that are forming in your beaker, right? So let's go through these examples. What mass of solute will dissolve in 100 grams of water at the following temperatures? Potassium nitrate at 70 degrees. So potassium nitrate, let's find that first. So that there's a curve at 70 degrees. So we find 70 and we're going to take it up, and where it hits the curve of potassium nitrate, there it is, and you want to take it all the way across as straight as you can, right around there, and I said that's about 125 grams. What about sodium chloride at 100 degrees? So we're going to find sodium chloride right here, 100 degrees, up, and that's right around 40 grams. Last one, ammonium chloride at 90 degrees. Ammonium chloride is here at 90 degrees, right there. That's about 65 grams, okay? Determine which of the above three substances, so out of these three, which one is the most soluble in water at 15 degrees? So I want to know at 15 degrees, so there's 15 degrees, which one of these is the most soluble? So here's sodium chloride at 15 degrees, and then ammonium chloride at 15 degrees. And what else did I say? Potassium nitrate at 15 degrees. So potassium nitrate at 15 degrees, we can only dissolve maybe about 17 grams. For ammonium chloride at 15 degrees, we can dissolve about 29 grams. And sodium chloride, we can dissolve about 38 grams in 100 milliliters of water. So out of these three, which one is the most soluble in water at that particular temperature? Sodium chloride, all right? That's the one where we can dissolve more of, okay? Let's take a look at our practice problems. At 80 degrees Celsius, the Hulk dissolved 50 grams of ammonium chloride in 100 grams of water. Did he make a solution that is unsaturated, saturated, or supersaturated? Well, let's find ammonium chloride. Here's ammonium chloride, and Hulk dissolved 50 grams of water, or 50 grams of ammonium chloride in 100 grams of water at 80 degrees. So at 80 degrees, we are right here, okay? So originally at 80 degrees, you can dissolve about 59 grams of ammonium chloride in 100 milliliters of water. Well, at this temperature, if he dissolved 50 grams, which is down here, right, is that considered unsaturated, saturated, or supersaturated? That's unsaturated. Because think about it. If a saturated solution is 59 grams of ammonium chloride can be dissolved in 100 milliliters of water, and he only dissolved 50 grams, he could dissolve more. What if he dissolved 70 grams? So up here. So he went way above, right? If you're only able to dissolve 59 grams in 100 milliliters of water and he dissolved 70 grams, then he made a supersaturated solution. Now here I'm showing you a supersaturated solution. If you see on this, I don't know if you saw it or not, but there's a small crystal on that scupula there. And he puts it into the flask, and you see that? Isn't that cool? So he basically boiled this solution. This is sodium acetate, I think, and he boiled it and he added the solute in there. So at first it was a saturated solution, and then he cooled it down. And think about it, if he were to cool it down, then at that moment he actually has a supersaturated solution, right? There's too much in there at that one particular temperature. And so he added just one more crystal to that at a cooler temperature, and that's what happened there. Okay, so how would Hulk make a saturated solution at 100 degrees for ammonium chloride? Well, at 100 degrees right there, he would need about, 72 grams? So he would dissolve 72 grams of ammonium chloride in 100 milliliters of water. Number 2, at 40 degrees, how much potassium nitrate can be dissolved in 200 grams of water? So potassium nitrate at 40 degrees, it's right here. Okay, so you can probably dissolve right around 42 grams of water, but what do you notice about, 42 grams of potassium nitrate in 100 grams of water, but what do you notice about this question? I'm asking you in 200 grams. So what did I do with the water? I doubled it, right? So what would you do with the amount of solute that can be dissolved? You would also double it. So we have 84 grams that can be dissolved in 200 grams of water. Number 3, a saturated solution of potassium chlorate is formed from 100 grams of water. If the saturated solution is cool from 80 degrees to 50 degrees, how many grams of solid are formed? So let's find potassium chlorate right here. And it's saying that we cooled it from 80 degrees right here to 50 degrees right here. So at 80 degrees, we were able to dissolve, 40 grams, right? So 40 grams at 80 degrees. And then at 50 degrees, you can only dissolve 20 grams. So this is like the video that I just showed you. So if you cool it down, how much will come out of solution? Well, 40 minus 20 is equal to 20 grams, right? Number 4, how many grams of sodium nitrate can be dissolved in 50 grams of water at 50 degrees Celsius? So what do you notice I did with the water here? I cut it in half, right? So let's find sodium nitrate, 50 degrees. Originally, you can maybe dissolve around 112 grams. So you cut that in half, and that's about 56 grams. That can be dissolved in 50 grams of water. Which salt is least soluble in water at 20 degrees? Well, let's find 20 degrees. And which one is the least soluble here? The first one that we hit here, least soluble, that is potassium chlorate. Why does ammonia decrease in solubility from 0 degrees to 100 degrees? Well, why is ammonia the only one that's going down? What do we talk about? If the temperature increases and this is the only one going down, that tells us that this substance is a gas. And that's it for solubility of a solute.